Alright, hi everybody. So today we're going to talk about the periodic table. I'm going to do my first video with you. So as you can see, if you haven't noticed, here I am on the screen in the corner. Um, I'm trying out some new software. It allows me to project my webcam at the same time as I also show you my iPad screen. And so what you can see on the screen here is a periodic table. This is my dream backyard table. It's actually at, I think, the University of North Carolina. They have this beautiful periodic table to sit at and eat your lunch in the chemistry department. But really, what I'm hoping to do is to give you an understanding of how great the periodic table is. Because in reality, the organization of the periodic table, although it was done many years ago, it still kind of holds true. And the new discoveries that scientists make about the elements, they actually sort of fit into where they are on the periodic table. We kind of saw this with the last chapter when we looked at the S, D, P, and F sublevels and how they're all sort of grouped together on the periodic table. The main goal in understanding the periodic table, besides all the silly, memorization stuff, really is to understand how or why elements behave like they do. So let's get into a little bit of history about the periodic table. And the first scientist that really was important for organizing elements was Mendeleev. And Mendeleev, he actually organized elements based on atomic mass. And so his driving force was looking at how elements were reacting with different elements, particularly with oxygen, and organizing them, and seeing that when he did do this, the elements generally were organized in or based on their atomic mass. But there were some discrepancies, and you can see this on the periodic table. If you follow along and look at the atomic mass of each of the elements, you can see that there's some ones that are reversed. Argon and potassium come to mind. Iodine and I believe tellurium come to mind. So what we do today is we organize by atomic number, and that's what Moseley did. He organized by atomic number. And from this, we derive what's known as the modern periodic table, periodic law. And that says that when elements are organized by increasing atomic number, there will be regularly repeating patterns in their properties. And so today we organize the periodic table based on atomic number, and that is the modern periodic law. Now when we do this, we end up with two with two different organizational type setups. One is the group, and the group, it's just a vertical column. In your periodic table, on the regents at least, the groups are numbered 1, 2, and so on. And they're numbered 1 through 18. And what we see is that when you look at these elements in the same group, they have the same number of valence electrons. So elements in the same group have the same number of valence electrons. And what that leads to is, that leads to a situation where they have the same chemical properties. So take a look on the right here of the slide, and you'll see that lithium, for example, has 1 valence electron. Sodium has 1, potassium has 1, rubidium has 1. And that's because they are in group 1. In group 2, the elements have 2 valence electrons. And we see this going across. If we look at the group, and then we look at the valence electrons, 1, 2, and then we skip to 13, 14, 15, 16, 17, and 18, they will have 1 valence electron, 2 valence electrons, 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and 8 valence electrons. The only one that's an exception to that is helium. Helium is in group 18 and it has 2 valence electrons. But it still behaves like those other noble gases. Now we can also see in the periodic table that there's something called a period. A period is a row going across. And I've mentioned this before in the previous chapter. I talked to you about how, those are the number of energy levels. And that's what the period shows. So we see here, if you're in period 4, if we zoom into potassium, I don't know why my iPad is not acting right, but if we zoom in here to potassium, there are 4 energy levels in the electron configuration. Now, the periodic table that you'll get won't have those electron configurations. You'll be responsible for figuring them out on your own. So, why are some of the elements in the same period? And again, that is because they contain the same number of principal energy levels. Okay, I'm going to pause the video for 1 second. It's like a crazy bird outside. I just want to close my door. Okay, so when you're in a period, you have the same number of principal energy levels. And so you can see those elements in period 4 have 4 principal energy levels. In period 5, they have 5 principal energy levels. So what about those periods that are separated from the rest of the elements on the periodic table? And so this first group here, or first period here, this is called the lanthanide series. And that's because lanthanum actually starts them off. For some reason, your periodic table starts them off with cerium, but in fact, they start with lanthanum. And then the actinide series. That is the lower group right here, or lower period right here, actinide. And so the lanthanide and the actinide, these are the F block elements. Now, something that you need to know, and there's some memorization in this chapter, you have to know which elements are metals, nonmetals, and metalloids. And so when you look at the periodic table, the metals are on the left-hand side of the periodic table. The nonmetals, they are along what's known as the staircase. And when you look at a periodic table, they actually outline the staircase. And these are the metalloids, excuse me. And then the nonmetals, these are to the right of the staircase. There's one exception for the nonmetals, and that is hydrogen. Is over to on the left of the periodic table, and that is because it has 1 valence electron, but in reality it's a nonmetal. Now these metalloids that are on the staircase, there are 6 of them that you need to know. There's boron, there's silicon, there's germanium, there's arsenic, there's antimony, there's antimony, which is Sb, and there's tellurium. So these 6 are the metalloids. They have properties of metals and nonmetals. You also need to know the gases, liquids, and solids. So the gases include group 18, and then 5 others: hydrogen, nitrogen, oxygen, fluorine, and chlorine. The liquids, there's only 2 of them: bromine and mercury, and the solids are all the others. Now you can make any element into a solid or a liquid, and most elements into gases, but this is at a specific condition called STP. So at STP, the elements exist at either gas, liquid, or solid in the following lists here. Now here are some images of the elements at STP. So this gives you an idea of the different properties, and it's worthwhile looking this over. It's a great book that actually has these all listed out, and you can look at each one and they give you details. This is from that website. So I just want to go over the names of the groups, and then I'm going to stop this video for now. So some group names, those include, for example, group 1 are called the alkali metals. Group 2 are the alkaline earth metals. Group 17, the halogens. And group 18, the noble gases. 3 through 12 are called the transition elements. And it turns out that actually only 3 through 11 really exhibit transition element type properties. Group 12 tends to just be metallic, they're not considered transition elements. Transition elements do things like have colored solutions when you dissolve compounds containing them in water. And so, some of these, the group 12 elements don't do that. All group 3 through 12, though, are in what's known as the d block. And those are elements that have their d orbitals being partially occupied as we go across the periodic table. So in the next video, I'm going to talk about details about the different properties of the groups, and I'm going to describe to you what I mean by atomic structure. Alright, so thanks so much.